Hello, my name is Spencer Sheen, and I am creating this video tutorial on how to make a 3D graphic such as this one that shows Ohio population density. I first started making these graphics as part of the 30-day map challenge in November. And I got pretty good reception on social media. And I even had people asking me for some video tutorials on how I create these maps. So making video tutorials is something that I've thought about in the past, but I'm using this as my nudge to go ahead and do it. So this is the first one. So bear with me if I meander and if it's not quite up to snuff. But I'm going to walk you through the whole process here as sort of a live coding endeavor. So I'm going to, all the way from downloading the data to setting up the graphic and doing the render and then adding annotations. We're going to walk through the whole process. So let's see how this goes. Now, first of all, I have created an RStudio project. I guess I'm taking it as a given that you know that I make these graphics in R. But if you don't, I make these graphics in R, and I'm assuming that you have a basic level of understanding of R. You've downloaded RStudio and you're familiar with the language and you're capable. So I'm taking that as a given right off the bat. So I've already created this project. I've called it the Kontur Rayshader tutorial. I'll share this project on GitHub, so everything will be available. I'm just going to make sure I have a clean slate here as we're getting started. Now, the first step is to download our data. And to make that Ohio graphic, I first heard about this data, like I said, from the 30-day map challenge, and it was the Kontur Population Dataset Day. So there was a specific day where they pointed us to the Kontur Population Dataset, and it's massive. It's a dataset for the whole world. So I've really just been taking different slices of it and creating what I think will be interesting visuals, interesting graphics. So that's what we're going to do today. I showed you a map of Ohio, but I'm going to make a map of Florida during this demo. So first things first, let's download the data. And you can download the data by going to Kontur. You can just Google search Kontur Population Dataset or go to Kontur, KONTUR.io. Takes you to their basic page, and if you scroll down a little bit, you'll see the population data set. And there's a button here, use for free. So we're going to go ahead and follow that link, which takes us to a download page. Now, this download page that we're on immediately is the global population density. This is a massive data set. I have had struggles loading it onto my computer. So I haven't even gotten past that step using the full global data set. So I would recommend you work with subsets of it. And you can find subsets, as you see here, the per country subsets. So there are subsets of the data at individual country levels. And like I said, I'm going to create a map of Florida here during this demo. And so we'll want the US population subset. There's also some information here about the methodology that they've used to create these population estimates. So you can review that if you're interested as well. But I'm going to follow this so we can find the per country subsets of the data. And next, we're just going to search for the country we want. And there we go. It's the second one that pops up. Now, the United States itself is still a pretty big country, so this data set is also kind of big. So it takes, on my computer, based on, I've downloaded it a couple times now, and it ranges from like a minute to a couple minutes. So I've already downloaded it, but you'll want to go ahead and download this data set. and you will want to save it to your R project. And I have already done that. So you'll see I've created this data folder in my R project. And within the data folder, I've just dropped this geopackage file. You'll notice the file suffix is gpkg. If you're unfamiliar, that's geopackage. I didn't know what that was before I started working with this data set. All this spatial mapping, I'm not a GIS professional. This is more of a hobby. I'm more, in my day job, more straight data analytics, but I love digging into this stuff. So once you have the data set loaded to your R project, now we can start to dig in. So let's create a new script. So the first thing we want to do is read in the data to our environment. So how do we read in a geopackage file? How do we read in this file? Well, lucky for us, there is the fabulous, fantastic SF package. And there's a function in the SF package that allows us to do this. And the function is called stRead. So I am going to use stRead. I'm going to pass the file path to this file and assign that to the data object. So data, Kontur Population, US 2022-06 30.gpkg. There we go. And this will take a second to load because, again, it's a pretty big data set. If it's not apparent to you right off the bat, there's some metadata included in the file name. So you'll see it's US, that's for United States. 2022-06-03, that's your date. Oops, didn't mean to click on it. So that's the date this data was released. All right, there we go. So we have the data loaded. Now, unless you're working with a small country, I would not recommend you start like trying to map it immediately because it's probably going to bog down your R session trying to plot that bad boy. Here, let's try to be good about commenting our code. So we've loaded the contour data. Next up, like I said, we want to map Florida. So the data object that we just created is the full United States. So next, let's load the states. And we can do that with the Tigris package. The Tigris package has a lot of geospatial, it makes a lot of that data available for the US. It links up to some census APIs. I think it's census. But anyway, some sort of API. So we have, I'm going to call this object st for states. And there's literally a states function in the Tigris package. Now, the states, you'll see there are 56 observations. That's because it's all 50 US states plus 6 territories. So we want to filter that for Florida, and I can't remember what the column name is that we need to filter on. So let's check it out. Oops. And of course, we're going to use many of the packages in the tidyverse. So let's just go ahead and load that up. There we go. Okay, so this name, the name column is the one I'm going to filter on. So we're going to filter name equals Florida. Boom. And oops, I don't want Florida, I want Florida. And let's remove Florida. Okay, so we see Florida is one observation. So that looks right, but let's go ahead and plot this bad boy and make sure we're on the right track. So ggplot plus geom_sf. Cool, that looks good. So the next step after this is we're gonna want to do an intersection. We're gonna want to basically filter this data for only those points that are covered by Florida by this polygon definition. And with the SF package, you can do that with an StIntersection function. So I'm going to call this object StFlorida. These names are kind of arbitrary, as you might have guessed. It's just kind of a habit I've gotten into of calling them these. Okay, so we're going to do an StIntersection. And this is going to throw an error because we did not match the CRSs. So the CRS is the coordinate reference system. So you can take a peek at the CRS with the function stcrs. So that shows you the CRS definition for data, and we can do the same thing for Florida. And you can see, without even going into the details of it, you can immediately see that they're different. So to do an intersection like this, they have to be the same. So you can make them the same with another SF function called stTransform. And we're going to say CRS equals stCRS data. So what this is saying is whatever the CRS, the coordinate reference system, is for the data object, transform this Florida object to that CRS. So now I just plotted it under that new CRS, and it looks pretty much the same. If we go back to the previous plot, you can see it shift ever so slightly. Now we should be able to do the intersection. So our next step, we can keep scripting as that's working. Just don't execute anything in the console. Our next step, well, hang on. Load states, filter. Let's be good programmers and comment our code. Filter for Florida. Check with map. Do intersection on data to limit to Florida. Okay, so next up we are so I'm looking ahead a little bit because I'm going to map this using the Rayshader package. The Rayshader package is a package for 3D visualization in R, and the primary type of data that Rayshader ingests is the matrix format. So we want our data to be in a matrix format. Now to translate it to a matrix format, I'm going to need to tell it how many columns and how many rows of the data, what that transformation needs to look like. Put another way, I'm going to need to assign an aspect ratio to the matrix. I think that's maybe a more intuitive way to think about it. And we can do that by based on the bounding box, the spatial bounding box that is created here. So let's say define aspect ratio based on bounding box. And you can see this is still working away, so we're still waiting on that. But you can get the bounding box. Let's assign bounding box to the BB object. stBbox is the function that will give us the bounding box definition. And we want that to be this object. So it's going to be stFlorida but again, still not executing. So hopefully I'm not screwing this up yet. It's kind of hard when you're scripting and you can't execute and make sure there are no errors. Okay, so the bounding box will give us, oh, there we go. The bounding box will give us 4 positions. It gives us the X min, the Y min, X max, and Y max. So using these 4 positions, we can calculate the 4 corners of a box that encompasses this area. And so we can use those to calculate the aspect ratio of this. Or put another way, we can calculate the ratio between the width and the height of this area. But this gets a little in the weeds of converting to spatial elements, so bear with me. First, we're going to we have to convert these numbers back to point coordinates, and we can do that with StPoint. So StPoint, BB X min. So let's say if we're taking X min and Y min, that will be the bottom left corner, right? And what's that do? We got a problem because I did not make it a vector. So if you look at StPoint, you need to pass in a vector of coordinates in the dimensions of those coordinates. We need to, so that's fine. And then we need to, so that's just a point coordinate, but it's not technically a spatial object. So we still need to convert it to a spatial object, and we can do that with STSFC. And now it's a spatial object, theoretically with the CRS. But this says CRS NA because we didn't define the CRS for it. So let's go ahead and pass in the CRS as well. And again, that's just the CRS of the data object. And there we go. Okay, so that's one point that that's giving us. Let's call it bottom left. And now to get the width, we need to calculate the distance between the bottom left and the bottom right. You could do it with the top left, top right also, but you probably know that. So then bottom right is going to be the same thing, StPoint, C, combine X max. And we're still sticking with the Y min because we're still on the bottom there, if you imagine your rectangle. And then STSFC CRS equals STCRS data. Cool, cool, cool. So now we have a point. Again, these are just points. I can illustrate this by bottom left. I can plot it, ggplot. Here, actually, let's start with Florida again. Here, I'll add it to the script. ggplot plus geom_sf. Boom. That's going to plot Florida plus geom_sf data equals bottom left. And there, you can see the point plus geom_sf data equals bottom right. Color equals red. There. So you can kind of see what we're doing here. So now let's calculate the distance. So let's call it width. I'm trying to think if that's going to create problems for us. We'll see. Let's call it width and ST distance. Bottom left, bottom right, boom. And then what is our width object? Okay, this is showing us the units are in meters, and it's about 847 kilometers. The reason it knows that it's in meters is because that's defined in the CRS. If you were to look at the StCRS, if you were to, again, review the CRS of data, you can see that it's telling you the length unit is in meters. Okay, so now we need to do the same thing for the height. But we don't need to do two more since we can base it off of one of these. So let's go from the bottom left to the top left. So do it along with me. We're going to go from xmin, xmin, bb y max now. So many brackets. Okay. ST SFC CRS equals ST CRS data. Boom. Okay. Now height is ST distance. Kind of type with purpose too. I forget about that. I hope it's not too annoying for you. So we're going bottom left again and top left. Okay, so let's say width is greater than height. True, so it's wider than it is tall. Width minus height by about 30,000 or 30 kilometers. So pretty close actually. So usually when I'm making these plots, I'll be reusing scripts. So I could hard code in what the aspect ratio is, but it's smarter to use, I prefer to use something that's more functional across different scripts. So let's handle different conditions. So let's say if width is greater than height, then we'll say W ratio, as in width ratio, is 1. And H ratio is height over width. So that's if width is greater than height. There are two other possibilities. Either height is greater than width or they're equal. And both of these can be handled by this condition. We'll say H ratio is 1 and width ratio is width over height. And in the case where these happen to be equal, then this would be, this would end up being 1, so it would be 1 to 1. All right, let's see if that works. It did. It's always good to run your code and not have any errors. So we see our W ratio is 1, our H ratio is 0.96, so they're pretty close together. Okay, well, I forgot to comment this again too. Okay, so let's, well, I kind of commented it up there. Width or height being the longer side. All right. So now we need to define our matrix. Now, currently our data is in a spatial format coming from this geo package. I don't know how to take that directly to a matrix. Perhaps there's a way to do it, but I do know how to convert it to a raster and then from a raster to a matrix. And the way that I can rasterize this is with the stars package. So let's go ahead and load the stars package. And now I'm going to call this ST Nope, I'm not going to call it that. I have never said that out loud, but I use that variable name pretty often. Let's call it rat. Yeah, rat. That's fine for raster. Rast. Yeah, cool, cool. Florida rast. How about that? All right, so the function we're going to use here is StRasterize, and we need to pass in the SF object. So that's going to be our, what did we call that? StFlorida. Oh, and I want to comment this. Matrix. Okay. So we're going to convert it to a raster, but we want to define the size of the raster. And so if we look at the definition or the help of StRasterize, I don't know why these help pages hang sometimes. We look at this ellipsis object or argument here is going to be, that's going to be what is passed to STS stars. So let's look at STS stars. And what we're interested in is NX and NY, because that's going to define the width and the height of this object. Put another way, it's the number of cells in the X direction, number of cells in the Y direction. Okay. So I'm going to say NX equals, I want these to be whole numbers. That's why I'm using floor. And let's just say size equals 1000. So 1000 is going to be our base. And so we'll say size times W ratio. So that whatever the longer size is using this method will be given the full amount of size. So here it will be 1000. But our NY, the height, size times height ratio, since height isn't quite 1, then it will be slightly less than 1000. It'll be the 964. Let's see if that works. Oh, I didn't run this. It's always nice when it runs without errors. I love it. All right, so there we go. We got Florida Rast. Now let's create mat. And mat is what I always call my matrix. And this, I always forget about this, but if you look at the Florida Rast object here, this is a raster, and it has 3 different vectors or elements: population, A land, A water. I believe that's area land, area water, but in any case, we are interested in the population variable here. So if you just pass, I point that out because if you just pass Florida Rast like that, you're going to run into trouble. It's going to create a massive matrix. That's not what we want to do. What we want to pass is specifically the population element. So we do that, and then we also want to define the number of rows and number of columns using the same thing we did up here. This is one of those things I'm always like, is it faster to copy and paste, or is it faster to just type it out? All right, so that worked. Now let's plot that 3D thing. Really clever tonight, guys. Matt. All right, so this is a basic workflow you can use to create these graphics. With Rayshader, first you want to plot it in an RGL object. You want to create the 3D model of it, the 3D object. And then we're going to use a function called render high quality. And it's going to take that object and it's going to ray trace the heck out of it and make it look really cool. But first we need to create this 3D object. So that's the step we're doing here. And so the first element is our matrix matte here. And then we need to height shade matte. And so we can do that using all the defaults just by doing with that code. I'm at the bottom of the script. I don't like that. And then we're going to pass it to plot 3D. Now let's take a look at plot 3D. Oh, it would help to load the Rayshader package. Okay, so plot 3D, it's looking for a hill shade and a height map as its first two arguments. So the hill shade is going to be passed by this height shade function. But then we can define height map is our matte matrix. And let's just see what that does. Ooh, interesting. So this probably doesn't look like much of anything. If you look at the shadow down here, you can kind of see it's the shadow of Florida. But you can also, this is an interactive window here. So you can click on it and move it. You can see we were viewing the object from an angle. And so there's a lot of things going on here. You can see the height here is really exaggerated compared to the dimensions on the XY axis. There's also a solid base. There's shadows being applied. There's a lot, all that kind of stuff going on. So let's adjust. The argument that affects the height exaggeration is the Z scale argument here. Which there's some, it's defined here for you. That was kind of confusing to me until I started playing around with it. So basically, the higher you make the numbers, the less exaggerated the height will be. So let's make it 100. Oops. Here, this is a good lesson. You want to close your window every time you're creating something, because now look, I've plotted over that last plot. So let's go ahead and close that. And there's this code you can add, rgl.close. Just as a reminder that you need to close the window if it's not closed yet. Ah, so that's looking a little cooler, right? This is what we're kind of trying to do. And if you pull it down, you can see there, yeah. Now we're on a better, this is closer to what we would want. It's not totally exaggerated, but it's exaggerated enough that this is going to cast some cool shadows and really highlight those areas of population density. We can clearly see that this is the state of Florida. Now, something else, these are all just my preferences I'm about to go through. So keep that in mind. You obviously can do whatever you want, but I like to make it not solid. I did it again. And so you can see the difference there. That's what it means by not solid. It's not creating that base under all those bars or those hexagons. Here, I'll take that out and do it again. Ah, I did it again. Got to close that window. So again, there you can see there's a base to this. That base is the solid. That's what it means by solid. And so I want solid to be false. All right. And I also so you can see the shadow is a bit below where the bottom of all of these hexagon bars begin. And the way that I've been creating these maps is like those bars are coming straight out of the ground. So there's no distance between them and the bottom. And you can set that with the argument called shadow depth. But shadow depth is actually, it's based on the depth in units of your data. And what I mean by that is, let's look at the range of mat. Their NA's values are present, so we have to do NA.remove. Okay, so we can see the range of our matrix, which again, it represents population density, or the number of people that are estimated to live in each individual hexagon. So it ranges from 1 person to 9,000 people in Florida. So if we want our shadow depth to be right at the bottom there, let's try setting it to 0. All right, that's pretty good. That's closer to what I want. Now, you'll notice that we're using just the standard green color here. Now, I always like to change the colors. You, I'm sure, will want to as well. There are many different ways you can go about it. One way that I recommend, one art package that has a lot of different, a lot of cool color palettes, is called Brewer by Blake R. Mills. And so if you want to follow me with this, you want to follow me exactly in this, then you can download the Brewer package, or you can find your own color palette you want to use. So I'm about to show you how we can do this. And I'm going to try this Hiroshige color palette. Let's see how that does. Do I want to do that, or do I want to try something new? What if I did something like O'Keefe 2? That would be pretty cool. Let's try O'Keefe 2. Let's try that. All right, so I like to, you're gonna wanna load these above where you're creating this 3D object. So let's create our color palette. And I'm gonna be using Brewer, so let's spell library right, Brewer. All right, so let's call this C1 is Brewer O'Keefe 2. Is that what it was? I also like to use the color space package. So load that because it has helpful things like swatch plot. So this is what our color map will be. And then technically, if you look at, so we're going to we're going to assign these colors in this function, the height shade function. So let's look at what the height shade function actually wants. It's this texture argument where you assign this. And you can see by default, this is how that green palette is defined. It's with this function here. So let's just steal this function. Why don't we? Let's say texture is, and then let's base it on C1, 256. I feel like I did that wrong. Swatch plot texture. Cool. Yeah, that's pretty good. You can adjust, you can play with this by adding the bias argument. For instance, if you bias it up, it will bias it towards the right. So let's say bias 2. You can see now it's more on the darker side. If we were to bias it to 0.5, it goes the other way. But let's not add a bias right now. Let's just leave it normal and see what happens. Now we need to pass this texture to the texture argument of height shade. Let's see. I can get down with that. That's pretty cool. Oh man, there's some high bars right there. That's one thing about these population estimates is they have some 400-meter areas that just end up being way overestimated. And it's something they note in their documentation if you look at that. I don't know, that's not totally sitting right with me, so let's bias it up a little. It's a little better, a little better. Well, let's see where we can go from here. All right, next thing, we want to change the angle. We need to have the angle set exactly how we want it when we pass this to render high quality, because it's going to render the object as it's shown in the window. So that is render. Now render camera allows us to adjust different elements of the computer, or of the view or camera, the view we're taking here. So if we look at render camera, there's theta, phi, zoom, FOV. So theta is the rotation angle. And what that means is if we put theta equals 0, then there's 0 rotation here. So it's like the up is north for these maps. So it's not rotated at all. It's just its standard, how it was translated to the matrix. The matrix. And then, all right, phi is, I keep wanting to say pi there. That is not correct. But anyway, it's the azimuth angle. So if we set it at 90, for instance, we're going to be looking straight down on this. Now, this is a 3D object, so that's not really what we want here. We want to highlight the different elevations of the bars. So let's cut that in half. All right, there. Now we can kind of see the different bars heights. And we need to zoom in a little bit, so let's adjust the zoom to, let's try 0.6. Oh, that's too far. Let's try 0.8. That's better. Okay, so now we have a pretty good zoom. But the thing about this angle we're taking of this state, the peninsula is where most of the action is happening here. And the peninsula is primarily north-south. So I don't want to look at it from a primarily north-south direction, because it's masking these different elevations that are found along the coast. So I actually want to change this 0. Let's go -20. And you can see that's turned us now. So the thing that I'm keeping in mind here as I'm setting up the scene is I'm going to be casting shadows. I'm going to create a light source that's going to cast a shadow. So if I were, for instance, to create a light source over here, it would have rays going this way. So it would be casting shadows like that. So shadows from this Miami area would be going like that. Is that what I want? I think it is. I think that would be good. What usually doesn't work so well is when all the shadows are being cast over the center of the state. So like if we had shadows coming from this direction or light coming from this direction and it was casting just over that. But let's try going the other direction and see what that's like. I think we need to go a little further. That might work. Then we could, I don't like that angle. I don't really have much reason other than my own gut about the aesthetic of the thing. So that's all I could tell you. So I think that is a good angle. And then I'm imagining I'm probably going to have a light source coming down like this. So it's going to be casting shadows going like kind of at a southeasterly angle like that. All right, so next up, now that we have that, we can start with our render high quality call. And now the thing about render high quality is when you're rendering a really high quality image, it's gonna take a while to render, probably like up to an hour, maybe more. So you want to get all your ducks in a row before that point. And you probably want to do some test renders first. So that's what I'm going to do. I'm going to do some test renders and try to dial in all the different elements that I want. Now, let's look at what we have to pass here. Render high quality. First point is the object name. You don't always have to define an object name. It could return your object here. But in practice, I found that I really prefer to define the object name. So I'm actually going to create a new folder called images. And I'm going to assign the file name images / let's call this test plot. Okay, so that's the first argument. Now light direction. These are the default arguments for the light direction. So we can go ahead and keep those and see what it looks like. So let's just let's keep most of this pretty basic and see how this ends up. Somewhere I can, well, let's just try it. This shouldn't take very long, I don't think. If it does, I'm going to quit this because it shouldn't take very long. You want to be able to iterate on this pretty quickly so you're not wasting too much time. Yeah, there we go. All right, so that just created this plot. Now you can see it's not super high quality. That's because we didn't make it, we didn't increase the pixel size of it. But this is giving us, what I'm looking at now is how are the shadows being cast? How do I like that? How is the lighting? Am I happy with the lighting, the direction of the light, the color of the light? Also, am I happy with how the color map is showing up? So how all of this is appearing. And I think I am. I think that's okay. I want to adjust the lighting though. Let's try to adjust the lighting. Also, I don't like it when it's interactive. That's just a personal thing for me. Okay, so then if we go back to, okay, light direction 315. Oops, I need to open the file back up. Okay. I think that's a pretty good angle. So the 360 and an angle of 360 and 0 would be pretty much straight. It would be up here at 12 o'clock. So 315 is going to be over here. Obviously, you can draw the line from the shadow and see that's your vector of the light. I'm happy with that, I think. But one trick I like to use is you can create multiple light sources. So we can keep light direction at 315, but let's play with the light altitude. Let's say one of these is at 40. Well, no, let's make it a little more dramatic. Yeah, everyone loves the drama. So I'm assigning 2 values here to light altitude, and that's going to tell render high quality that I want 2 lights. And now let's define the light colors. I want one of these. I want the high one to be a white light. And I want the low one to be R. If we look at this again, oops, this one. Let's try it with, I don't know, this color, the second color in this palette. And then white. And let's adjust the intensity. So then if we go back to the help page, we see that the light intensity was 500 for this. So I want the white light, I want that to be a little less intense, I think. So let's try, a lot of this is trial and error, so let's just give it a shot. Let's see what that does. Oh, I like it, I like it. So I like to add the colors that kind of match the colors of the palette because it makes things really pop for you. And actually, as we're doing this, I'm realizing I think we should rotate the light source a little bit. If we rotate the light source a little more, then we'll be more in line. We'll be able to see the light kind of reflecting off of these taller pillars. I think that would be pretty cool. So if this is 315, this is the light source is at an angle of 315. And let's say, so this would be 360. 360 minus 90 would be 270. I think 270 might be good. Maybe 260. Let's try 260. Let's see what that does. You can see this is the size of this image here. This is the standard size that it's creating. This is a small image. Ooh, you can already tell. You see what I mean by how the light pops? The light's really popping off those. That's pretty cool. That's pretty cool. I'm happy with how this is going. But what I was just saying is this is the size of the image. And because this image is so small, there's the pixels per inch, the resolution is not very good. So what we're going to do is we're going to increase the resolution of everything when we're ready to do our final render. And then that's when this step, this render high quality, is going to take much longer. So that's why we want to do all this work to hone it in now. There's one thing I don't love here. This kind of it's kind of like these shadows are like perpendicular to the coast. I don't love that. I wish they were a little bit of an angle. So let's I said 270 and then I changed it. So let's try 280. Let's see what that does. And then once we have it at 280, all right, I'm just gonna let it go. I'm not gonna waste too much time on this. Yeah, much better. Okay, that's gonna finish. Now, like I said, our step here is to increase resolution across the board. The way that I do that is I first hop back up here, and I'm basically going to change the base size. And then I'm going to rerun everything else. And I'm going to make one other adjustment too. Well, actually a couple other adjustments. So first, let's try a size of 6,000 and see how big the matrix ends up being at that size. And when I say how big, like how many bytes. Because in my experience, I have a ceiling that I don't want to go past. And you can already see this is taking longer. And we're upping our memory usage here. This shouldn't take that long. And that reminds me, let's save this file, because this is where you can start to crash your session. Main. All right, let's try it again. I'm really surprised it's taking this long. That makes me think it's a bad sign. Something is amiss. It shouldn't be taking this long. So here I'm just hitting escape to try to quit the process. Maybe if I close RGL. So now I just closed our window. Let's cut it in half. All right. That's still, so usually my limit for the matrix is around 200 megabytes. So I want to push this. I want it to go bigger. You can do it, MacBook. I haven't mentioned that yet, I guess. I'm on a MacBook Pro with an M1 Pro chip, 32 gigabytes of RAM, 10 cores. So I have some decent capabilities here, nothing outlandish, you know. All right, so now Matt, so I've set the base size to 5,000, and that ends up with a matrix. Our buddy Matt, right under 200 megabytes, so that's fine. I'll just leave it at that. And let's see. Then just run through all of this again. Oh, our Z-scale is going to be off. So we had our Z-scale at 100, but we just increased the resolution of the base map by 5, by a factor of 5. So we can adjust our resolution or our Z-scale to keep it the same as it was by dividing this 100 by 5, so it'll give us a Z-scale of 20. So let's try that. I made this map too, by the way. It's pretty cool. Really like this desktop background. So you can already tell this is taking much longer than the other one. But you can kind of see this has giving us much better resolution of the data. And it's because we increased the resolution of our raster, which in turn increased the resolution of our matrix. So it's all trickling through. Now I'm just waiting for this to finish its render. You'll know that the render is done when you see the shadows. There's a lot more you could do with this rendering, this plot 3D. You could do other shading. There are other ways you could shade the map. And that would all happen here in this window instead of using render high quality. But any of that shading is done by render high quality itself also. So you don't really need to worry about that if you're just planning on doing a graphic with render high quality in the end. So now we need to adjust the camera again. And there we go. Everything looks good, I think. Were we rotated more? Did I throw off our rotation now with the higher resolution? No, that's about the same. Do you think we should try a little bit more? Maybe just a little. Just a little bit. No. Okay, let's go back. Now, I don't want to call this test plot anymore. Let's call it final plot. And there's another argument to update. There are several other arguments to update here. First of all, so to increase the resolution, the quality of our final graphic, of this graphic, there are a couple ways to do that. There is the, where are they? Okay, so it's arguments passed via the ellipsis, and you can see those are passed to rayrender render scene. So let's take a look at that. Okay, here we go. So you have the scene, which is defined. It's the pixel width and the pixel height. There are all these other arguments too. So for instance, setting interactive equals false, that's passed here. Let's see, there's another one. Where is, oh, samples. So samples here. If you read through the documentation, it'll tell you that increasing the number of samples will increase the quality of your image, but it will also increase the time it takes to render. And there's more information about what these samples actually are, but suffice it to say that I set samples, I jack it up to 450. 450 is pretty high. You can run into some trouble if you set your samples too high. You could have renders hang and just not complete. I've run into that. So be careful when you're doing it. Maybe work your way up because you might waste a lot of time. So increasing the samples will increase the quality, but also increasing the size. So if we look back at this, let's look at the info. This is 600 by 600. That's pretty small. So let's just jack that up by like 10. And let's say width equals 6,000, height equals 6,000, and that is going to be a much higher resolution image. Something else I like to do is to wrap all of this in its own sort of anonymous code chunk. And I do that because I can say start time equals sys time cat cyan start time. Oops, I don't want start s time, I want start time. So if you just run that and then you run that, crayon. So all I'm doing here is printing some helpful bits to the console because this render is going to take a while. So I'll run this whole chunk all at once. That's what happens when you do these brackets. And it immediately gets the start time. Let's go ahead and define our out file here, because another bad thing that can happen to you is the render doesn't try to save the file until the very end of the process. So if you're doing like a 2-hour render or something, and then it fails to find the file, then it just fails. So let's define the out file before our code chunk, and then if file doesn't exist, out file, let's PNG, write PNG matrix 1. Target equals out file. Okay, so what this is doing, let's just run that. That is writing a plot using PNG write PNG. And write PNG can take a matrix and write it to an image. And so if I just pass a matrix with a single value, it's a 1-cell matrix of 1, then that creates a 67-byte file image called final plot, like that. And so I'm doing that to ensure that this is a good file path. So either this file is going to exist, in which case this code chunk won't be executed, but I know the file's good, so we can continue. And if this file doesn't exist, then it will try to create this small file quickly. And if the file path is bad, it's going to fail here, and it won't continue here. So that's just a way to ensure that you're not going to run into errors further down the line. And then finally, let's get the end time. End time diff equals end time, start time, cat, crayon, cyan, okay. Now, if I have done this all correctly, when I run this code chunk, we have our object set up so it's ready to be rendered. We have our light sources set up. We're making it 6,000 by 6,000. So I think we are good. So when we run this chunk, it'll tell us the start time. If the file path is good, it will just start to render. And that's what we see. Okay, so I anticipate this will take about an hour. I'm not gonna sit here with it the whole time. So I am going to pause here and come back. It is late Sunday evening for me, so I will come back tomorrow morning and wrap this up. And we're back. It is now Monday morning for me. And we can see here that our render completed. So that code chunk finished executing. And it took, the units aren't displayed here, but this is 45 minutes. So it took under an hour. And that's honestly not very long for one of these renders for me. Like we saw, I was trying to up the base size. I tried to start it at 6,000, but I was having trouble creating that raster, so I gave up on that. So usually I would have a larger matrix, which provides more detail, but for this video, I didn't want to waste too much time doing that, so it didn't take that long to render. Let's take a look at what our final product looks like. So we can see that it was saved here in our images folder. We had been saving the test plot. So we can see the test plot there. We still have our RGL window open. Now let's take a look at final plot. Pretty good. Pretty good. And as we zoom in, this is a high resolution version, so this is taking a minute to update. It is not actually that blurry. My computer is being slow for some reason. What is happening? There, that's showing you the resolution a little better. So that's as good as we're gonna get with our render. You can increase the base size like I was just saying, and that might get a little better, but for our purposes, this is pretty good. This allows you to see pretty good definition. You can identify individual 400-meter hexagons within these areas. So I'm pretty happy with it. This will serve our purpose. So this is being pretty slow. So I need to free up some memory, I think. Let's go ahead and close this out. Close this out, close this out. Oh, and while I have renders going, this is a helpful command for you if you're on a Mac. There's a command called caffeinate, and when you run it, it will just keep your Mac from going to sleep. And so I run that when I have long renders going. I'm not 100% sure it works like I think it works, but my intention is that it keeps the Mac from going to sleep so it doesn't pause the render midway through. Okay, so now that we have our base graphic created, this final plot, we're done with this script. Now all that's left to do is to annotate the script. So we can clear our whole environment of all of this, close this out. And this is, I don't know why we're being so slow this morning. All right, oh, I accidentally just quit my whole project. Gotcha. I was gonna restart anyway, so this is okay with me. What did I just call that? Rayshader tutorial? No, this is wrong. Oh, I called it Kontur. Kontur Rayshader tutorial. There it is. All right, and we're back. So now we want to create a new script. So our next and final step is to annotate our graphic. Library. And the main package I'm going to use here is the magic package. Now magic uses a command line. It uses a tool called image magic, which is a command line interface tool to do a ton of manipulation of images. It's super useful. If you've never seen it before, I would highly recommend you look into it. I use it. I use the magic package in R, but I will also use the CLI in the command line. It's just really handy to have that capability. So if you search image magic, you can find plenty of documentation on it. So I recommend you look into that, but I'll walk you through how we can use it with R. So we've loaded the image magic package. The first thing we're going to do is we need to read in our image to the R environment. So let's call it image read. So the image read function, you're going to pass the file path. So that would be images/final plot. And there we go. Just for your information, if you were to just print image, it's going to display the image for you. It'll display some basic information about the image along with the image in the viewer pane over here. This is a large image, so it takes a while, but it shows you format PNG, 6,000 by 6,000, all this kind of information. And the viewer pane shows you the full image, which is too big for that. So if you open it in your browser, it'll show you this. Okay, I want to go ahead and clear that. Clear that. All right, so now we have our image read in. Now we want to do some manipulation of the image. And the way you can do that is by chaining or piping some commands together. So we can do image annotate. And the image annotate function will allow you to add text to the image. So this first argument image is passed by the pipe. The next argument text, let's call this Florida population density. The gravity is the starting point of where this annotation is going to be placed. And I say starting point because it starts there, but you can also add another argument called location, which will make an adjustment based on that starting point or that anchor. So let's start with the north. And so the options are northwest, north, northeast, east, southeast, south, southwest, west, and center. I think those are all the options. And they go around like the cardinal directions would. So it would be northwest is top left corner. North is going to be just centered in the top of the image. So let's just start with that. And then as I build this chain, I found it's faster to work with the final image instead of waiting for it to display on the viewer. Like if I was just to execute this, then it would be trying to display that image in the viewer. But instead, I'm going to go ahead and write this to an image so that I can just view the image in max preview. I'm going to call it titled final plot.png. And let's see what that does. Takes a minute because it's a big image. There we go. Titled final plot. Where is our text? Oh my. Look at how small that is. So the text is there, but it is very, very small. Actually, our image is really big, is what's happening. So we're going to need to do something about that. So let's make this bigger. So we can say size equals, let's try 250. Let's see what that does. I'm going to start doing multiple commands before as I update the image, just so this goes faster. I'm going to adjust this. I'm actually going to do this from the northwest because I think just looking at this image, there's some space over here above the panhandle the way this is tilted. So I'm going to have the title over here. And I'm going to crop this image as well. So let's say northwest location equals 200 plus 200. And the way that this works is the first argument, I think it's plus 200 plus 200. So the first plus 200 is telling you move right from the northwest corner 200 pixels and move down 200 pixels from the northwest corner. And these location arguments are always relative to where you set the gravity, so that can get a little confusing. But let's go ahead and try that and see how we feel about that final graphic. I need to crop this. It'll go faster once I crop it. This is also a great thing about working on a Mac. The preview pane just updates when the file is updated. I love that. It makes it so easy to do this kind of stuff. All right. Now, one other thing, I don't want this to be black. I don't really like the black color of the text. So I'm going to look back at main. I'm going to mimic the colors we were using here. So I need to load the library again, met Brewer. Let's call this colors. Oh yeah, and color space. There we go. And to get a good contrast on this background, we're going to need this to be one of the darker colors. So I'm going to go the full, so this is 1, 2, 3, 4, 5, 6, 7. I'm going to go to the last color by saying colors 7. Okay. I'm also going to go ahead and crop this. And again, we're going to set the gravity and the geometry. So when I crop, I think it's usually easy to set the gravity to center and geometry. This is a little tricky because again, it's the syntax unique to ImageMagick. So our image is 6,000 pixels across. And I think I want to maintain that because there's not a lot of room on the width. There's not a lot of padding along the width. So I'm going to say 6,000. But there's plenty of extra space in the height. So I think we can go down to 4,500 actually. Let's go ahead and try that. And I think that text is probably too big. So let's go smaller. And let's just see what that does for us. All right, that's a little better. I think we can even go a little tighter in terms of the height. And of course, if your intention is to create a print of this, if you want to create a poster or something, you should keep in mind the dimensions that you're setting. You probably want to set it to a more standard print definition. One thing, I think this color of the text could still be a little darker, so I'm going to darken it. And the way you can darken is with, again, the color space package has a function called darken, go figure, colors 7, and I'm going to darken it by 0.5. Well, that's kind of dark. Let's go to 0.25. And then if we swatch plot text color, then we can see that's a little darker than that. So I think that will be good. Like I said, we're going to tighten it up on the height. So I just removed 500 more pixels. So it's now 6,000 by 4,000. I also want to use a funner font than this standard font. So let's look at, again, I'm on a Mac, obviously, but I'm going to look at my font book and see what I have. I've downloaded a lot of these fonts from the internet, a lot of them from Google Fonts, which if you're unfamiliar, Google Fonts, I wonder what that would look like. Rayrender. Font equals Rayrender. So while that's loading, I can show you. If you're unfamiliar, you can go to fonts.google.com, and there are many fonts that you can just download. A lot of times you don't have to download them either. You can just point to the URL here. So there are plenty of ways to do that. In R, there are packages that help you do that kind of thing. All right, so there we go. That's kind of a flowery font. Not sure how I feel about that, actually. Let's keep playing with fonts. I don't want to spend too much time on this, but I want a different font than that. Let us see. Dr. Seuss is pretty fun. All right, I'm gonna look at, I can't find the font I'm looking for, so let me check a different portrait or a different graphic like this that I've done to see what font I was using. So for instance, for a Virginia graphic, if I look at the markup script, El Masiri, okay. Let's use that. I know what was happening here. If I go to all fonts, then I'll find El Masiri. There it is. So it's a basic font. Yeah, I like that. For the title, let's make the weight of the font bold, and you can do that by setting the weight to 700. I also want to darken that a bit more, so let's go ahead and darken that so it's a little darker. And while we're at it, let's add another layer here to add our data credit. So let's say data from Kontur Population released 2022-06-30. And I know that's when it was released because of the documentation, but also because the file name here. That's the point of this file name. But where do we want that to be located? If we look back at our graphic, I think there's room on the bottom here. Let's try the southwest. Gravity equals southwest. Let's match location equals plus 200. So that'll align with our title, plus 100. So the 100 will be coming up from the bottom. Let's use the same font. And let's make the size much smaller though. Let's say the size is 80. Ooh, and let's set the color. Oh, that's what was happening there. I didn't update the text color. Okay, and let's set the color to, let's set an alpha for the color to make it not pop off the page. Let's kind of hide it a little bit. So we'll do text color 0.5. All right, let's see what all that does for us. So library ggplot2. I think alpha is part of ggplot2. Yeah. So the alpha function will add an alpha transparency element to the color hex code itself. And there we go. So I think I darkened this too much because I was incorrectly not updating this text color. So I want to fix that. All right, so we added that annotation. Let's also add a credit to ourselves. Graphic by Spencer Sheen. And I'm going to throw my Twitter handle in there too. And I'm going to use the same, all of the same stuff here. But the one thing is I'm going to move this up 200. So the location will be an extra 100 pixels above this line. And so this is one annoying thing about, or you might find this annoying working with ImageMagick and annotating graphics like this instead of, for instance, just, you know, creating a text box here and typing in your stuff. But I find I prefer to have it all scripted out so that I just find it easier. I prefer it. And it's much easier to reuse scripts than, whereas if you were just creating this graphic again and you would have to toy with all of that again. Okay. Now, what else can we do? Let's, oh, I didn't. Spelled that wrong. There we go. Now, one final piece of annotation I want to add is a little descriptive text. And for any time I'm adding longer text like this in a script, I like to use the glue package because it makes it easy to do multi-line character strings. And you can also use interpolation, but I don't think I'm going to be doing any interpolation here. So I'm just going to say this map shows population density of Florida. Population is bucketed into 400 meter, about 1/4 mile hexagons. Population estimates are bucketed into 400 meter or about 4¼ mile hexagons. And then I'm going to use string wrap to ensure that this text is wrapped and it's not just along a single line. And I'm going to set the string wrap it. Let's try 30. And let's add this annotation here. Annotate gravity. Let's set the gravity here to west. let's set the location to, oops, equals plus 200. So if it's west, it's going to be coming like right here. So let's try to put it like somewhere over here. So we probably want to go plus 1,000. Because remember, that graphic is 6,000 across. Plus 0. Let's see what that does for us. And then color equals text color, size equals 150, let's do 125. Font equals El Nasiri. And so if you don't have this font, you can use whatever font you have, obviously, or keep the default. And I spell this wrong every time, apparently. And I need to execute that. This is why I just load tidyverse usually. String RR. There we go. Okay. So now we're getting close. Getting close. All right, that's pretty good. I think I can increase the text size. I think I can make this one bigger. I think I can make this one bigger. I can let this width here be wider. I need a space there. We need to go down. So this is a good example. So I've set the gravity to this text annotation to the west, and so I moved it over 1,000 pixels, and I've adjusted the Y with 0 pixel adjustment. And so if I want to move it down, let's move it down 500. I do that by saying plus 500. If I wanted to move it up, I would say minus 500. Oh, that's big. Oh, what did I do there? Oh, I made it 250. I meant to go 150. Whoops. All right, and I think the credit text down here is a little big for my liking. And I actually think I want to try it in the southeast. I want to put it in the bottom right corner. See how that feels. And so one key piece that I haven't mentioned yet is I'm starting with the base graphic. The base graphic is final plot. And then I'm chaining all of this annotation together and writing to a different file. So if I were to do this and overwrite my original graphic, then I would only have one shot at this. So it's really important that you're working on a separate out file. You're writing this to a separate file. There we go. Okay. I don't like this over here now that I've done it. So a few things I still want to change. I want to move this text back over here because I think it will flow better to have the text. The reader of this will naturally read the title and then this annotation here, and then having the credit text below that I think is more uniform. I also think I can crop this a little bit further. So we'll try that. So what if we crop it to, if we take another 500 off? But I want to take the 500 mostly from the bottom. So here, we're gonna, first let's change that credit text. Southwest. And if we're gonna take it from the bottom, then we can add a location to our image crop call by appending it to the geometry string here. So I don't want to adjust anything on the X, on the width aspect. So I'm going to say +0, but then I want to move it down. Right? I want to move it down 250. This is kind of hard to imagine, so let's just do it and see how that works. As I did that, I think I'm going to need to move it up. So a -250, but we'll see. Yeah, that was the wrong way. All right, that's pretty good. I think I moved it too far down though. So let's adjust, let's say 150. Okay. Now that I've cropped it a little further, I think I can make the text a bit smaller. So let's say 125, let's say 200. And I can move this, I think I can move that up a little bit. All right. This is feeling pretty good. Let's take one more look. I feel like I could, since this has one word going to the next line, I feel like I could adjust this to maybe fix that so that it looks a little more uniform. That's a little better. What if we, feels like it's crowding in a little bit over here. So let's move it left. Yeah, let's move it left a couple hundred. Oops, that's the wrong one. Let's move it left a couple hundred pixels. And I'm still not happy with where this is. I didn't like it over here either. So maybe what we should do is, instead of doing two lines like this, let's just set it at one line. And we can do that. Let's just combine. Using glue again. And I'll separate them with this space, slash space. And then we can get rid of this whole annotation. And we can move this to center. And we don't want to move it on the x-axis at all, so we'll just move it up 100. And let's see what that does. Feeling good here, feeling good. I think this might be it. Ah, that was not it. Not center, we want it in the south. And I can also move this. I want to move this further over. I want it to be like over here. So let's move it, let's see, plus 600. Okay. There we go. I think I'm happy with that. Last step is to proofread everything. Make sure you haven't made some dumb spelling mistake. So we have Florida population density, looks good. This map shows population density of Florida. Population estimates are bucketed into 400 meter or about 1/4 mile hexagons. All right, all looks pretty good to me. Graphic by Spencer Sheen at Mr. Peckner's. Data from Kontur Population, released 2022-06-30. All right, I think we're set. So hopefully this has been an instructive video. I'm gonna plan to do more of these because I thought this was kind of fun. And it's helpful to me to vocalize what I'm doing because it makes me be a little more critical and thoughtful of how I'm going about things. So I'll do more of these videos. I'll be interested to hear your feedback. So if you have questions or Other feedback, please leave them in the comments below, or feel free to shoot me an email or message me on Twitter. I'm at Mr. Peckners on Twitter, spencer.sheen@gmail.com. You can find me there. Anyway, thanks for watching.